This is the second video for section 3, and it's going to involve the disk method to find volumes. So what I want you to consider is maybe we have a graph of some sort of a function here. I'll just try to put something in here like so. And we want to find the area under the curve between these two vertical lines. What we could do is just put in a rectangle like we've talked about and put in a bunch of rectangles and just calculate the area. But what if I said I want to take this shape that's made by this area and rotate it around or revolve it around that horizontal line there, this line that's right here. So I'd get a volume. And what I could think about doing is taking these rectangles that I'm drawing in, rotating them all around, finding their individual volumes and adding them together. So it's taking the concept that we did with area, but now doing it with the volume. And when I rotate this rectangle around, I'm going to get this sort of a shape. What we could think of as a cylinder or maybe a disc. And we would have a bunch of these discs lined up here, and we just have to add up all the volumes. So it's the same sort of idea as adding rectangles together. We're just going to add a bunch of the discs together. So if I were to label this rectangle a little bit, let's say that, because we're dealing with a cylinder here, this part right here we could just call a capital R for a radius. And because this base is kind of going along the x-axis, we could maybe just call that thickness dx, if that helps us. So what they're calling example 6 here is what's the volume of the cylinder on the right side there. And so the volume would be the area of the circle. So we'll say area of circle times that width, or I guess the height of that cylinder, which would be a dx. And if we wanted to simplify that or come up with a formula, the area of the circle is pi times capital R squared, and then we still have the dx. So that's the general thing to take here, is that it's always going to be pi times radius squared with a little thickness to that thing, which we call dx. And a lot of times that capital R is just going to be a function. It's whatever equation we're looking at to make this overall line right here. So a couple formulas here. If we were to look at a function that's kind of going along like this, and so we need to rotate that around, our rectangles are going to be going this way, and we're going to be rotating around a horizontal line. So one thing to note is that whatever line we're rotating around, the rectangles will go perpendicular to it using this method. And so the formula is going to be an integral from whatever our limits are there. We're going to start at A and go to B. We're always going to be rotating that radius around, or that rectangle around, so that's the r squared part. We have a pi there for the circle, and then a little dx. So the integral really means all these rectangles that I have listed right to the left of this and to the right of this, now add them all together, fit as many rectangles as you can underneath, and eventually we get the perfect volume. And we could also do this if we wanted to rotate. Maybe we had a function that's going like this, and so now it would make more sense to rotate around a vertical line. Our rectangles then are going to be horizontal. Horizontal. And so again, perpendicular to the axis of revolution. And so now we just have a dy there. Instead of r of x, it's going to be r of y, because what we're looking at here is an x value in terms of a bunch of y things, but we still have a pi there. And so it's still the same basic idea. Our variable here would just be something in terms of y in the end. So I'll show you a few examples, and I think that will help it make a lot more sense. So let's say that we were looking at this shape, and I know you have maybe a more complicated picture below this, and it just doesn't copy well. But we want to find the volume if we rotate this around the x-axis. And so, I'm probably doing a little bit more than what the instructions are asking for here, perhaps. But if we're going to rotate this around the x-axis, that means our rectangles would have to be perpendicular. So my rectangle might be something like that. Okay, so how do I find the area of that rectangle, or maybe not area, I shouldn't say, but how do I find the that rectangle being rotated around the x-axis? So what I'm going to do is say, what's the volume for just that slice? How would I figure it out for just that slice? So I'm going to have a pi times the radius squared with a dx. Remember, the radius is just the height of this rectangle. So how would I think about that? Well, that's whatever that y value is, and y equals 4 minus x squared. So for this particular slice, my formula is going to be pi times, that function was 4 minus x squared with a dx. And then if I wanted to, I could, I need to square that, right? Because the radius is 4 minus x squared. I actually need to square that radius. And then if I want to simplify it just a little bit more, I could actually FOIL that out. So I'm going to have a pi times a 16, and you can go through and do the FOIL, but I get a minus 8x squared plus an x to the 4th with a dx. So in the end, that becomes the volume of just that slice, and it depends on whatever the thickness is, whatever dx, before I can figure it out. Now, if I take that idea and I fit as many rectangles in there as I can, so the dx's become really small, but I have infinitely many rectangles, I get the perfect volume. And I can represent that using an integral. So the total volume then, or maybe we could say perfect volume, would be that same idea of a pi. Now, pi is just a number, and then I'm going to integrate from 0 to 2. Now, why is it from 0 to 2? Because those are the x value limits. Because my rectangles are vertical, and so it's a dx instead of a dy, I want to go from 0 all the way to 2. And then it's just going to be that same function. So a 16 minus an 8x squared plus an x to the 4th, a dx. And then we just need to go through and integrate that. So this would be undoing the power rule. And so I would get pi, and then a 16 to the x minus, and then I'd have an x to the 3rd. It means I need to multiply by 1/3, so it would be an 8/3 in front. I would have an x to the 5th. It means I multiply by a 1/5. And I put the limits at the end, so from 0 to 2. Okay, if I were to calculate that out, if I were to plug a 2 in there, I still have that pi out front, but I would have a 16 times a 2, which is 32. I'd have a 2 to the 3rd, which is 8, and 8 times 8/3 would be 64 over 3. And then 2 to the 5th would be 32, so that means plus a 32 to the 5th. I suppose I should, maybe I'll have a big parenthesis out there, because now I need to subtract what happens when I put a 0 in. Well, if I put a 0 into any of those pieces, I get a 0 out, so it's just going to be like that. And then I just need to think about what would happen when I put all these fractions together, and that can take a little bit of work. Just remember common denominators. I think with these kind of values, you would maybe need a calculator to figure that out. But you get 256 with a pi there. Remember that pi out front, over 15 would be your answer. For the next example, we're still finding the volume, but now we're going to rotate around the y-axis. And it still suggests that we draw in that rectangular strip just to help us think about this. So if we are going to revolve around the y-axis, that means our rectangles should go perpendicular to that. So my rectangle will look more like this. And so note that now what I'm measuring is actually an x value. I want to know how far to the right I'm going. So if this is the equation, I would need to rewrite that in terms of x equals. So if you went through and you did the algebra on that, if you actually squared both sides and then moved the 16 over or somehow swapped the x and the y, in the end this equation would be x equals, oops, let's grab the right thing there, be x equals the square root of 16 minus y squared. So if you don't trust me, either jot down a question saying, hey, show me that in class, or actually try doing the algebra and solving for x there. So again, we need to figure out the volume of just that slice. If I were to take that red rectangle and revolve it around the y-axis, what would the volume be? So the volume of a slice, there we go, volume of a slice should equal a pi times the radius squared times, in this case, a dy because of how the rectangles are running. And again, the radius is going to be the length of that red rectangle. It's whatever x value I'm reaching for that particular spot. So what does x equal? X equals the square root of 16 minus y squared, which is the radius, so I need to square that yet, and I get a dy. And if I were to simplify that, I just get pi times 16 minus y squared with the dy. Okay, so I take that idea, and now I'm going to find the volume of the total shape if I were to do that. So I fit in as many rectangles as I can. The dy's get really small, but I'm fitting in many, many, many rectangles. So that's this whole integral idea. So pi is a constant. It can just stay on the outside. I have to think of my limits. Well, because I'm dealing with a dy, I want to know the y values as I move along the y-axis. So I start at 0, and it looks like I'm going all the way up to 4. So from 0 to 4, and it was 16 minus y squared, bean squared. Whoops, I take that back because that canceled out. And then we have a dy. So again, I would need to undo the power rule in this case, and I definitely think that's something that you should know how to do. But just for the sake of time, know that that's a skill you should have. The answer for this would be 128 pi over 3. Okay, the next example is a little bit more complicated because initially they don't give you the picture. And I already took care of that, but now they're just going to tell us some of the limits for the area that we're looking at. So it's bounded by y equals 2, which is right here, by y equals 6, which is up here, x equals 6, which is right here, and then this equation, x times y equals 6, which, if you think about it, you could just rearrange to y equals 6 over x, and then if you were to plug in a few x values, you can get these y values, which I've plotted, and you just connect and you get that kind of shape. So the area that's bounded by all of those, so we're really thinking about this area right in here. First thing they say is revolve this around the line x equals 6. And so this gets a little bit more complicated because now we're starting along this line, and I have to think of my rectangles going out this way. So whenever I measure, I have to make sure that I'm measuring from here going out to the end of that rectangle. So we do the same process as before. I want to find the volume of a slice. And so it's going to be pi times the radius squared with a dy. And so how do I describe the radius? How do I actually think about the distance from here, from the axis of revolution all the way out here? Well, I do know that the distance from here to here is 6. And so I could think about it as 6 minus this little piece right here. And so this chunk right here, I can just call that x. I want to think about how, here, I'll just write it down here. It's going to be 6 minus x. I just have to think about how do I describe that x value. Well, that x value right here is related to the curvy function. So it was x times y equals 6. If I could just take that and solve for x. Now down here I solved, down here I solved for y. If I just rewrote that, but I wrote it as solving for x, I get x equals 6 over y. And that's going to be what would represent this x value wherever this rectangle is along this axis of revolution. It's always going to be related to this relationship here. So instead of the radius being 6 minus x, I can write it as 6 minus 6 over y. And that's really what I want here because in my idea for a slice, I'm dealing with the thickness being dy. So this becomes my radius. That is a complicated idea, so jot down some questions if that's not clear. But in order to describe this radius, I need to start from the axis of revolution, and I need to figure out how to measure from here going to the left. So the easiest way to do that is to say all of 6 minus that little chunk right there. So my radius was 6 minus 6 over y. I'm going to square that and have a dy. And I could certainly simplify that a little bit if I wanted to. Now I kind of know that in this case I'm going to have a complicated answer, so I'm just going to leave it like that for now, and you'll see why in a second. So let me just kind of clear some space right here. So the volume of the total, so again the dy's get smaller because I'm shoving in many more rectangles. That's the idea of an integral, so I'm going to have a pi, a constant that's just going to go out there. Have to think about my limits. The lower limit for this shape is 2, going all the way up to 6 for those y values. So I'm going from 2 to 6. My equation was 6 minus 6 over y being squared. Then I have a dy after that. And then this is one that would probably be a calculator question just because the answer, well, it doesn't have to be, I suppose. We could do some of this by on our own, but it does get a little bit more complicated, and the answer for this one is, that's a 2, can you believe that? 241.588 if we were to use our calculator for it. And our last example, second part of this question here. Now we're going to revolve the same area, so still this space right here, but now we're going to revolve it around the line y equals 6. So we're starting from way up here and drawing this way. And what I want you to notice here is that it gets a little bit more complicated. There is a change right here, and now my rectangles will be kind of bounded by two different shapes. Initially, it's from 6 to here, and then over here it's from 6 to the curvy equation. And so we have to actually set up two separate integrals for this, so it gets a little bit more complicated. So for this one, we're going to try and jump right away just to the total volume. But for that first part, I want to understand that the limits go from right here all the way to here. That's from 1 to 3. So the area or the volume of that shape would be pi in front. I'm going to go from 1 to 3. And then to figure out what that radius squared is, remember that I need to start at my axis of revolution and go this way. And so I could think of it as going a total distance of 6 minus whatever this y value is. So that would be, get my pen back here, it would be a 6 minus that y value, and I know that that y value is just, because it's that curvy equation, it's going to be 6 over x. So 6 minus 6 over x, I need to square that and have a dy. Okay, to that I'm going to add the volume of that second shape. And so now the limits are going to be from right here all the way to the end. So this is from a 3 all the way to 6. And I could think about that the same way. What is the overall distance? Well, starting from here and measuring, I certainly could say, well, 6 minus this, but I can actually figure that out because now it's 6 always minus 2, because this entire distance right here is at 2. So in the end, it's just 4 if I wanted to write it out that way. So I get a 4 squared with a dy, because that was always 4. So there's actually something here. We could have a shortcut for this. If you kind of notice that, it's actually, when I rotate this, I just get one big solid disc or cylinder. I wouldn't even have to do an integral if I didn't want to. But again, ask a question on that if you don't quite catch that. But if you went through and you calculated both of these integrals and added them together, your overall volume would be 203.889. Okay, copy that down. I'm sure there will be some questions, so be ready to ask in class.